So as you can see straight away, I changed the title. I found my own title way too long. And I really think we are at the peak of inflated expectations when it comes to AI-driven drug discovery, which is, of course, a very exciting space to be. I'd like to think it's as excited as being on top of Mount Everest. But if we imagine all of us being up there, it's also quite a scary place to be, because the only way from here is down, one would think. So in this session, we are going to look at ways that we will make sure that we can stay up on top for as long as possible, up to the point where we can actually deliver new treatments for patients. It's working. So what is it that we are all here trying to do together is to make people better, ultimately. And I looked at this thinking that surely it's not going to be something very exciting, but I was quite surprised to see such a high percentage of deaths are due to disease, especially with the news around accidents and war in national television. If you look at the causes of death, 9.9 people out of 10 will die of disease. So I think it's fair to say that we've got our work cut out as a community to deliver better treatments for patients. But for that, we need to be able to understand the data we have. And I think it's fair to say that we are living through a data crisis, which wasn't such a big problem before as it is now, with AI attempting to use the data we've got and make conclusions that would help us to move forward. So this is a publication from Nature, 2016, and they asked scientists to honestly declare their ability to reproduce published data. 70% said that they struggle with that. And I think what's even more surprising is that 50% even admitted they cannot reproduce their own data. And I think that's a really tough ask. I'm not sure what the reward for that was, but it's definitely anonymous. And I wouldn't dare to ask this audience to raise their hands, because that wouldn't make it anonymous. But I personally have struggled previously to reproduce data as simple as a Western blot when it comes to kinase signaling, for example. So as a result of all of this, we spend an extortionate amount of time in the lab as scientists. 80% is what people self-declared. Probably the rest is lunch and toilet breaks. So where is the time to think? And overall, to move from a target to a clinical candidate, if you're very lucky and you make it to a clinical candidate, is around 5 years and costs around $2 billion. So how can we make this better? Well, one would think use technology that's available. Oh, my luck has run out. OK, I'll switch. So the challenge is actually Moore's law is stipulating that computing power is growing exponentially. And this has proven not to only be true, but actually underestimation. Computing has been improving during our lifetime beyond exponential curve. However, Erum law, which is a palindrome of Moore's law that somebody really smart came up with to mock us all, is actually showing that for drug discovery, the trend is the exact opposite. So what we do is we are spending double the money every 9 years to develop a new drug, and we are failing to actually make more new drugs. So we are using technology, but if anything, we're getting worse for it. We spend money on it, and we don't get the benefit out of it. And I think we could all wonder why that is, but the easiest place to look is the very basics. So what tools do we use to generate data? No, I don't think I have a pointer. So enzymes, just to begin with, you get a kinase, and you could say that the scientist is really poor at reproducing their own data. They are bad scientists. No, they are working with the truncated enzyme, very often with unknown activity. And that's absolutely normal. That's what's available to us today. That's what we've got to work with. So as you heard in the first talk, how important it is to have a full-length functional kinase that's crystallography grade, all of your experiments will just simply be much better. The second big issue, in my opinion, and that's quite shocking, is 1 in 5 cell line vials that you take out of the freezer is mislabeled. We're not talking about genetic drift, which you can imagine from Gila. It makes perfect sense, right? She died several decades ago, absolutely normal for the cells to drift. No, it could be a wrong vial labeled as Gila that you're holding in your hand, confusing you all along your drug discovery journey for not fitting in with your hypothesis. And then the third, and I think probably the most important of these all, is that the kits are sold fairly purely QC'd, and there's huge batch-to-batch variability that, again, the providers don't have to declare, and we usually find out really the hard way. And the only way to prove this is to use robotics. So you're excluding human error, which is what we do at Arctoris. So then we can go back to the providers and say that it has to be your reagents that are faulty. Second, protocols. I am not sure who's recognizing this protocol. It's a protocol how to make tea, but it could well be a protocol how to make Western blot. And I've actually come across this for Western blotting. I have some questions about the milk. So if this is how we operate in the lab, how do we expect to generate data that's AI ready? We have to move away from this towards making biology more of an engineering discipline. And then the last one, which I'm not going to spend any time on because we are sitting in preclinical, is then to actually be able to, let's say you got all your rights, everything right, how are you going to translate to the patient? What model systems do you have available to you to be able to predict how these patients are going to actually respond to the drug? Incredibly difficult question, and one would call it the valley of death. That's again from Nature. They're very good with fancy titles. So I think all of it comes to, I'm a maths person, so I like to put equations on things. If you look at the pharma productivity equation, then essentially you can measure productivity as a function of progress. So shots, you need to look on the top right corner. Work in progress, shots on goals, multiplied by the probability of success, multiplied by the value, divided by the cycle time and the cost. Yes? So we know that cost has gone up quite significantly because we are investing in using today's compute, today's technology, but we haven't managed, and that's obviously bad for this equation because you have higher cost, which is on the bottom of the equation. So where you want to go is to decrease the cost by needing to do less testing, so making less molecules, doing less experiments, decrease the cycle time, so have lab in the loop and cut out white space, increase probability of success, so predict what's going to be successful, and also if you're predicting something to be failing, you can find ways to fix it before it actually failed, and increase the shots on goal, again assuming that this is a pharma budget that's remained stable. We should be able to, as a result of all of this, have more shots on goal and then ultimately get more drugs to patients at a lower cost. So the topic of the entire session's discussion is whether we are in a hype or in a trend. I think no matter which one we take, we are on top of a mountain, and we would like to stay on top of this mountain for as long as possible. This is the hype cycle for artificial intelligence, and there's a lot of arguments out there that it's actually not a single hype. It's a massive secular trend. So if you look across time, there was a hype around big data. Then 2017, a hype around AI/ML. 2020, a hype around lab automation. 2024, the Nobel Prize, and we're very lucky to have Mars here representing isomorphic. And now, are we moving towards quantum computing? Again, we have Kat talking about quantum computing in a second. And can we get to the place where we can use AGI, so artificial general intelligence, for drug discovery, but also in general for our lives? So I think if we look at all of these hypes together, we're talking about a trend, and I don't think anybody here would argue that this is not the direction where drug discovery is going. Now, it's fair to say it's mad out there. Funding is hard to find, but a lot easier if you have AI in your company name and if you're actually also using it. I don't have a pointer, but we add a tiny, tiny sector on the right-hand side in the pink. That's who we are in relation to the entire machine learning, AI, and data landscape today. And this is 2024. Now, when it comes to investments from VCs, large pharma, and this is not from me, this is one of the pharma companies presented it, and I took it, is looking at it as if they are in a casino. And I think we actually are all in a casino. So what we have are multiple multi-armed bandits. You don't know which one is going to give you how much reward. Each of them have a cost of pulling the arm. So what are you going to do? Are you going to explore? And then the first one that gives you a reward, you're going to stuck with it and you keep pulling? Or are you going to move on to exploiting? So straight away look at the shiniest one, the one that's closest to the door. I think I know what I do. And just go for that and keep pulling until it delivers something for you. So that's a big challenge at the minute on how to distribute funds. And I think it's actually a good challenge because it gives everybody an opportunity to be a multi-armed bandit that can play. So overall, what I would like us to look at is building foundational data sets, from which we can then build foundational models. Ideally get lab-in-the-loop situation going, where we can send experimental protocols to machines, so nobody can ask about the milk. That's not a question anymore. Shake this. OK, how to shake it, how long for, which direction, what frequency to shake it at. It always has to be the same. Or even just something as simple as room temperature. I'm not talking about -10 degrees, but I'm talking about 20 or 22 or 25. Is it a heat wave? Is it winter? What is room temperature? How do we define that? Because all of the enzymatic processes will be slightly different depending on the temperature you run them at. Then ultimately, we would get to a multimodal infrastructure. And this is where I think human in the loop is going to be super important. Let's keep the scientists. I think somebody referred to it as good old science. It's important to have scientists who have time to think. And then hopefully, we get to hacking the pharma equation and then reversing Eroom's law and then actually deleting it from the vocabulary, because I find it quite offensive to all of us as a community. Now, what Arctoris does is supposed to be a video, but in the name of high tech, it doesn't work. So I'm going to have to show it to you. We essentially built what we call modular automation, which sounds very fancy. But in reality, what it means is instead of having one high throughput unit that can run one experiment, extremely high throughput, but fixed, always the same way, one input, one output, we have put robotic arms in between stations, which makes it modular. So if this video was to work, it would be an arm that would be moving plates from one instrument to another. And this allows for flexible workflows. That means that you can run experiments at lower throughput, but without having to give up automation as a benefit. So you can have reliable, reproducible data this way that's precise, and you can use later for model building. We cover 3 different disciplines. I'm not going to go into detail here. But ultimately, what we do are essentially 2 different things. One is large data generation, and you will see a couple of case studies of that. Another one is DMTA cycles, which are a perfect example of low throughput. So usually make 20, 25 compounds is what people make. For biologics, is 96, because that fits on a plate. Again, people will run it across a long period of time, and it's important that it's reproducible. If you lose your, and I see several people from creative disruption here, if you lose your golden-handed technician, will your DMTA cycle just collapse? Is that what we all want to do? Or do we want to have a robot in place that is never going on sick leave, is constantly there, overnight, midnight, Sunday morning? It will give you the same result as it does on a Tuesday, midday, when it can skip the lab meeting. So it just doesn't matter. You always get the same data reliably throughout the years. I think that's a very important thing to consider when we think about automation. We just need to make it affordable. And then the third thing